Okay, we start again for the final session of this workshop. I am very pleased to welcome Dr. Anaïs Dréau. Anaïs is a CNRS researcher. She works in a laboratoire Charles in Montpellier. And she did her PhD at the Laboratoire of Photonics, Quantiques and Molecular at ENS Cachan, that doesn't exist anymore, but now it's ENS Paris-Saclay, in 2013. She then went to do a postdoc in the Netherlands, and she participated to the measurement that you mentioned about the loophole-free Bell state loophole-free measurement with NV centers, right? And then she got a CNRS position. We are very happy with that 10 years ago. And Anaïs is approaching a very challenging and very promising topic. During the lectures, we discussed single photon generation, and I've shown you how using single quantum emitters, you can really generate efficient single photon sources. And everything, as I've shown you, are done in materials that are 3-5 semiconductors, the same that are used for laser pointers, for instance, or atoms, or etc. And what Anaïs is exploring is to do that with the king material of microelectronics, which is silicon. And the idea is that if you manage to do spin qubit, but also photon emitters in silicon, you may have a platform that scales easier because we already master this technology very well. So I think that's what I wanted to say. Hope I didn't forget anything. Yes, and so I'm very looking forward to your presentation to tell us about this journey of making silicon that is known as a non-light material become a very important one for quantum technology. Let's welcome her.
Okay, so good afternoon. So thanks a lot, Pascale, for the introduction. So I think you made a nice overview of where the topic is currently. And thanks a lot for the invitation. So I'm very happy to be here today to tell to you about single color centers in silicon. And those systems are new quantum systems that we've recently isolated and can now investigate a single defect-scale for quantum applications. Yes. Yeah. Okay, so color centers are called this way because they are fluorescent point defects. They can absorb light and change the color of crystals or gems. So for instance, here I took the example of a diamond. So if you incorporate nitrogen impurities in diamonds, their colors can change into yellow. Now, if you incorporate boron impurities, you can get blue diamond. And you can also reduce the concentration of those impurities down to typically 1 impurity atom per 1 billion of carbon atoms. And there you get an ultra-pure diamond. And this type of samples that we are using in the lab in our advanced microscopy using advanced microscopy techniques in order to detect those color centers as single defect scale. Okay, so what are the quantum assets of the system? So first we're going to start from a perfect crystal lattice in which I arrange periodically all these atoms. So those atoms are going to share their electrons and then going to form energy bands, one valence band and conduction band, that are going to be separated by a band gap, so forbidden region of energy. And now, if I'm creating a point defect, so for instance, I'm replacing one atom by an impurity, or I can remove one atom to create a vacancy, or I can also displace one atom to an interstitial site. So those point defects are going to locally confine the charges, and as a result, we're going to get a discrete spectrum of energy levels. And this is quantum. And now those systems, we can excite them with laser light, and they're going to relax by emitting photons, a particle of light. And that's why we call this system artificial atoms. And the advantage of this system is that here we don't need some complex trapping techniques to trap them into a vacuum. They're already trapped inside the crystal. So what are the quantum properties that are interesting for quantum applications? The first one, that if we are able to isolate those defects at single scale, we have a single photon source. So here, thanks to Pascale lessons, you know that we can use those photons to encode quantum information, and since they can really propagate over large distances, as we've seen in the previous talk with Hugues, that we can develop applications for quantum communications. And you can also decide to locally use those photons to process information in a quantum chip, and that's the field of quantum integrated photonics. And some of those defects can have an additional quantum degree of freedom. That is an electron spin on a zero electron spin, whose state can be optically detected. And now we can use this magnetic property, magnetic state, in order to encode, and process quantum information. And besides the use as a memory, the energy level of these spins are very sensitive to parameter changes in their environment. And you can use that in order to develop quantum sensors. And suddenly, sometimes you can try to assemble those two bricks together in a quantum way, and you create a spin-photon interface, in which the spin and the photons are going to share this very special quantum link that's called entanglement. And this opens applications for the generation and the building of quantum networks. So far, the most advanced color systems is by far the NV center in diamond. So this is called NV because it's made of a nitrogen impurity plus a vacancy. And this effect, you can excite it with a green laser light, and it will emit single photons in the red part of the spectrum. And why is it the most advanced color systems? Because it has been investigated at single defect scale for almost 30 years. So for instance, here you see really the first optical scan in which all the isolated spots correspond to single NV centers. And these color centers has really exceptional spin properties. And especially it's one of the rare quantum systems, matter quantum systems, that can operate at room temperature. So for instance, the coherence time, the T2, that correspond to the time on which we can preserve its quantum properties, which is 2 milliseconds at room temperature. And now there's there's two main applications that have been developed with this system. The first one is the development of quantum sensors. So, for instance, here you have NV scanning magnetometry, in which on each band you're going to use the spins, some magnetic structures, and reconstruct the magnetic field and make some magnetic images. And for instance, if you are rich enough, you can buy some kind of machine, quantum sensors, available since 2010. But there are also more physical quantities that can be probed with this system, like temperature, pressure, and electric field, and so on. So if you want to know more about the NV Center in Diamond, I invite you to go and see the seminar from Jean-François Roch. That's also a part of the series of Pascale's lessons. But the application I'm more interested in the building of a quantum network. So now if you cool down the NV Center at low temperature, you can get this nice spin-photon interface. And what we learned in Hugues' presentation is that we can use the photons to distribute entanglement between distant spins. And for instance, in the Netherlands, they were able to generate entanglement between two NV spins that were separated by 10 kilometers. So that is quite impressive, especially knowing that the NV Center is quite a bad emitter. And one reason why is because its emission occurs in the red part of the spectrum. So this undergoes strong attenuation in optical fibers, typically between 5 to 6 dB. And this is really exponential loss. So after a few kilometers, you are really left with nothing. So one strategy to circumvent that is to use optical nonlinear process of frequency difference generation and change the color of the NV center photons down to the telecom band where you have the minimum of losses in optical fibers. So this is doable, In fact, this convention process has been used in the 10 kilometers entanglement experiment, but still, it's also hard to do, and it's add an additional degree of complexity to a quite complex experiment. So that's why there's another strategy we can also try to follow, is to find other color centers that will feature the same interesting properties as spin properties as the NV center, but by emitting directly in the telecom band. And here we have a problem with diamond, because there's no infrared emitters in diamond. So currently, one explanation for that is that the diamond has very high energy photons, and those effects are likely to relax non-radiatively by emitting photons rather than photons. So that's why we are forced to investigate all the platforms for that. And that is not necessarily a bad thing, because diamond, you may know, but it's not an ideal material, and because it's not adapted to large-scale industrial and fabrication processes. And for instance, the size of the diamond sample that can buy for like single crystal ultra-pure diamonds is only a few millimeters like big. So ideally, we would like to have a platform that is adapted to large-scale industrial processes. So I'm asking you, okay, which material do you have in mind? And should all answer me? Yes, silicon, exactly. Because silicon, you can really buy wafers like 30 centimeters big, so you really consider the size of a pizza. And on this, you can really etch and nanostructure, for instance, transistors that will be the size of a few nanometers. So there's almost 8 order of magnitude difference. So when you think, okay, silicon is such a prominent material, there must be this material that must be investigated a lot, searching for single color centers. And in fact, this has started only recently, because we had to wait for 2020 to have the first report of an optical detection of a single color centers in silicon. And so the reason why silicon has been overlooked, we can directly see that here, when you compare its band gap. So it's a small band gap semiconductor, so compared to diamond, the energy scale is 5 times smaller. But you have two consequences. The first one is that those color centers, they do not emit light at room temperature. So to detect them, we'll have to cool down to roughly like 10 Kelvin. And secondly, for instance, if we use the same green laser as we're using for the NV center, here, the excitation is going to be slightly different, because the laser is going to create free charges and excitons that are going to recombine onto the energy level of the defect to create the light that we're going to collect. So I'm going to first explain you how we manage to detect single color centers in silicon. So we started from a silicon sample that have been carbon implanted. So we bombarded the lattice with carbon ions in order to create color centers and defects. After, we put that in our helium-closed cryostat, and this in an optical scan of the sample. And what is nice is that you see a lot of hotspots there. And we're able to isolate some very bright one. So now the question, is it a single color center or not? So to claim that, we have to analyze the statistics of photon emission. And for that, we're using the HPT or hand-buried run and twist experiment. So the principle is to send the photons toward a 50-50 beam splitters with 2 detectors behind. So there, if we have only single photons, it has either one chance of the 2 to be reflected and detected by the first detectors, or one of 2 chances to be transmitted and detected by the second detectors. So in other way, there's the 2 detectors cannot click at the same time. And with that, we can reconstruct the autocorrelation function versus the delay between the 2 photon detections. And what we observe is that at 0-bit delay, we have a dip. And this is called an anti-bunching. And what quantum optics tells us is that if this anti-bunching gets below the value 0.5, we have a signature of single photon emission. Hence, we have single emitter, and we can say that for sure it's a single color centers. Okay, that's great, because this is the first time that we discover some single photon emitters inside silicon. Can we have more? So we check at the PL spectrum of these defects, and we observe that all this emission is directly in the telecom band. And what you see here, you have a sharp zero photon line around 1.28, and this broad photon segment. And since then, the field of research about single color centers in silicon for quantum applications has been really booming. One reason is because silicon, and the other reason is because there's many different families of core centers, single core centers that can be isolated optically in silicon. So for instance, within only 6 years, there have been more than 11 families reported. And trust me, there are way more. It's just that we don't have time to investigate those. And you can directly see here the advantage of those emitters, that their emission is directly in the telecom band or very close to it. So we see the big improvement compared to end-center emission. And those defects are split into two groups. The first one are well-known confocal from the literature that have been investigated a lot on ensemble measurements previously in the previous decades. So you have the G centers, T centers, W centers, interstitial carbon atom, and erbium dopants. And we have also some defects that have never been reported in the literature. And those ones are unidentified. We don't know what their microscopic structure is. And this really illustrates the power of these new techniques, low temperature confocal microscopy, in order to reveal new defects in silicon, besides the fact that this material has been extensively explored and investigated regarding its defects. And in the recent years, there has been important progress regarding the spin control of those defects. So first with single erbium dopants, we're able to demonstrate for the first time the coherent control of the electron spin of single erbium dopants. So we see here the modulation of the fluorescence of the single defect versus the microelectronics length. And they achieve a coherence time on the order of 50 microseconds, and in addition, they were able to demonstrate a single shot readout, meaning a projective non-demolition measurements of the electron spin state. Oops, sorry. Regarding also the T centers, that is a carbon-related defect. So there they were able to demonstrate the coherent manipulation not only of the electron spin, but also of nuclear spins that can be either intrinsic to the defect or located at their vicinity in their environment. And recent article here managed to improve the coherence time and curatives on the order of 2 milliseconds for the electron spin and around 200 milliseconds for nuclear spins. So here, nuclear spins have naturally longer coherence time because they're much more protected from their environment because they're just like heavier. And using the electron spin of single T centers, they were able to generate entanglement between two nuclear spins. So in addition, the electron spins of two distant T centers have been entangled using their light emission. And in Montpellier, we also managed to coherently demonstrate the control of electron spin of another defect, that's called the G centers. So for the rest of my presentation, I'm going to mainly discuss about this defect. So the G centers is one of the most carbon complex in silicon. It's so frequent that it's even used as a measurement of the carbon concentration. It's used as a measurement of the carbon concentration in irradiated silicon samples. So to create a G centers, you start from a perfect silicon lattice, and you're going to take two neckboard silicon atoms and replace them by two carbon atoms that you can see here in black. And in between, you're going to incorporate an interstitial silicon atom, here in purple. And the two assets of the G centers for quantum applications, it's first a telecom emission. So here you see the photorescent spectrum of a single G centers. So here you have a sharp 0.09 around 1.28 microns. And in addition, you have another line here that's associated to a local vibration mode. And it's very important to have these lines because the ZPL of the G centers is at the same wavelength as the former defect that I showed you before. And at the beginning, those two defects were has been mistaken for each other. So you want to have this A-line to be sure that it's G-center, because the G-center also has a non-zero electron spin. And especially in the 80s, there have been this measurement of an optical detection of the magnetic resonance of the electron spins. And this was associated to a spin triplet that was not in the ground state, but in a metastable level. So for us, it's very important to have this ODMR signal, because it's a technique they can use in order to scale down the measurement down to single defect scale. And in addition, the G-center has a very interesting properties. It's quite uncommon. So if you look at its microscopic structure, you can see that the carbon atom, they have 4 bonds. So they're really rigidly attached to the lattice. But this silicon atom here, it has only 2 bonds. And as a result, this gave it a rotational degree around the carbon axis. So this is really an uncommon property, because usually most of all the color centers they are really like they have a static configuration, and there's no motion of their center of mass. But it's not the case of the G-centers, and we are able to demonstrate a signature, an optical signature of the motion of this atom on single G-centers. So for instance, on individual G-centers in SOI samples, so silicon on insulator samples, we observed an optical fine structures that is linked to this reorientation dynamics. And here, this rotation for those systems, for those defects, it's triggered by the Oberth-von-Gap excitation, by the green laser. And what it does is that at every optical cycles, the silicon atom will randomly hop between 6 possible crystal sites. So it's as if our G-centers were behaving like a ball in a 6-slot roulette wheel. So I don't know which kind of application we can do with that, but still it's funny to have, I think, the smallest casino roulette wheel on Earth. So in the recent years, research has been mainly focused on controlling the optical properties of G-centers. So for quantum applications, where we want to be able to tune the wavelengths of emission of our defects. And this has been done using star tuning by applying an electric field on a G-center ensembles in a PIN junction. And more recently, researchers used demonstrate strain tuning to change the wavelength emission of single G-centers in a MEMS cantilever. And also, there have been a lot of efforts in order to integrate those single G-centers inside photonic cavities. Because here we're in silicon, so the problem that the refractive index is high. So most of the photons emitted by the defect stay trapped inside the material due to total internal reflection. So in practice, even if you're using a high numerical aperture objective, you're going to collect less than 2% of the photon. So to improve on the photon count rates, you can integrate that inside photonic cavities. So these have been done on ensembles first, and after on single G-centers in different types of photonic cavities. And now I'm going to show you the results we got concerning the integration of single G-centers inside circular Bragg grating cavities. So these samples have been designed and fabricated by our collaborators at Sylvia Letty and Felix under the supervision of Jean-Michel Girard. So here, the confinement of the light is done in the depths using the difference of refractive index between silicon and the oxide. And here we're going to etch the silicon in order to create these rings, and that will act as the mirrors to confine the light inside. So we are able to find the cavities in which there's a single G-centers. We check that by measuring the autocorrelation functions. And here, compared to the former G2 I showed you, the purity is much better. and this is also like uncorrected data. So it's good because it means that there's very little noise polluting our single photon emissions. So now regarding the spectrum, here you only see one, the ZPL in the PS spectrum of the integrated G centers. And this is a huge improvement because before we were collecting 14% of the photons in the ZPL, and now effectively it's like 94%. And it's interesting because it's the ZPL photons are the only one that you can use in order to develop indistinguishable photon emission that is used for the entanglement protocol, entanglement swapping protocol. Now regarding the count rates, so this is the count rate, the saturation curves on the single G centers in unpatterned SOI, and this is the one we measured on this single integrated G centers. And we got roughly an enhancement by a factor of 30, but now we consider only the photons emitted in DPL, we have an enhancement by a factor of 100. Okay, so now we have our photonic cavities containing one single G centers, and this one is very close to microwave microstrip that we're going to use to generate the microwave magnetic field to control the spin state of this defect. Okay. So if we come back to the energy level structures of the G centers, so we have a ground state spin singlet, an excited state spin singlet, and after the metastable spin triplet. So if there were no interaction, these three states will be degenerated. In fact, the 2 ampere electrons are going to interact through spin-spin interaction, and that will lift the degeneracy between the three spin states. And this is described by the Dorothea splitting Hamiltonian, where you have a longitudinal parameter D and a transverse parameter here. And this one is going to mix the spin state ms plus minus 1 in order to create the coherent superposition plus and minus. And in addition, theoretician tells us that this state 0 is more coupled to the ground state. So it means that it has a shorter lifetime, and its population is going to decay faster to the ground state. And we can use this property in order to initialize and polarize our spin. So to do so, we're going to apply a laser pulse. We're going to put all the population in the 3 levels, and after we're going to wait for 5 microseconds for this state to decay in the ground state. Okay? After, we're going to apply a microwave magnetic pulse. So this is going to transfer the population from plus state to 0 or from minus to 0. Okay, and after something, we wait 5 microseconds and we apply a laser light in order to record the luminescence emitted by the defect. And this is the Odemer spectrum we got. So here we recorded the luminescent signal of the defect while sweeping the microwave frequency. And when the microwave magnetic field is at resonance with one of the 2 spin transitions, we get an increase of the emission of the defect by roughly 7%. And from that, we can extract what the value of the D and E parameters down in the gigahertz range. And those values are in very good agreement with the one extracted from ensemble measurements in the 80s. That's great because this is the first report of an Odemer spectrum, measured on a single G center. So now what about the coherent control? Because the coherent control of the G centers have never been demonstrated so far, neither on single defect, but not also on ensemble. So for that, we're going to use the same pulse sequence, but we're just going to tune the duration of this microwave pulse. And what we observe is these nice rubby oscillations that demonstrate the coherent manipulation of this single electron spin. So now what about the coherence time? So for that, we're going to create a superposition. So from one side between plus and 0 spin state, and from the other side between minus and 0 spin state. And what we do observe is these oscillations that decay on a time scale, and that correspond to the T2 star. So in our case, for the G center, we have T2 star around 1 microsecond for the 2 spin transitions. But here, you might notice another thing, that you have a frequency beating. So when you perform a Ramsey fringes experiment, you expect to have oscillations at the frequency detuning between the microwave frequency and the spin transitions. So if we had only one spin transition, we should have only one oscillation. And here, since we see frequency beatings, it implies that we have multiple spin transitions. And so indeed, when we compute the Fourier transform spectrum of these Ramsey fringes, we observed 4 peaks in the low frequency spin transitions and 5 peaks in the high frequency transitions. So why have we not seen those transitions in the first Audemars spectrum that I showed you? And here we can compare the splitting here on the order of like tens of megahertz compared to the line width of this spectrum. And here you can see that it's more on the order of 100 megahertz because the lines are power broadened due to the microwave pulse. So after we did the same measurements, but by increasing the duration of the microwave pulse and using less microwave power. And indeed, he done in those previous ESR lines, there were like four electron spin transitions and 5 electron spin transitions, and those frequencies here correspond exactly to the one recorded from the Ramsey fringes experiment. So now the question is, okay, what's the origin of this fine structure? So we might think, okay, it could be a hyperfine coupling to nuclear spins. So for instance, you can consider silicon-29 or carbon-13 that both have a spin 1/2, and this will result in the splitting of all the electron spin transitions. But here, due to the transverse the splitting interaction, this parameter here, that is going to mix electron spins, this hyperfine splitting is going to cancel. So you have no hyperfine splitting at zero magnetic field. That's why we can really rule out these explanations. And the origin of these fine spin structures is linked to this reorientation of the spin axis over time. That is the process is called spin tumbling. And the definitive proof of that is when we record frequency selective Rabi oscillations. So here we're going to record Rabi oscillations that will be like selective onto one given fine spin transitions. So for the low frequency electron spin transitions, we detect like the same Rabi oscillation. So here, nothing surprising. What's very interesting is when we do the same thing on the high frequency branch. And what we got is that for those, when we have a resonance with these two fine spin transitions, we record a Rabi oscillation that is roughly twice faster than for the rest of the spin transitions. So let's consider the formula of the Rabi frequency. So it tells us that this Rabi frequency is going to be proportional to the scalar product between the magnetic field and the spin axis. So the magnetic field is going to be fixed because it's imposed by the geometry of our sample. So if omega does change, it implies that the S is moving over time. And we've developed a model considering really the 6 possible positions that can take this interstellar silicon atom, and considering only simple geometric arguments, we can show that when the G centers in these two orientations, 0 or 3, it will experience a stronger magnetic field that will result in Rabi frequency that will be exactly twice faster than for the other side. And also for the specific position, for the low frequency branch, the magnetic field is going to be perpendicular to the spin axis. So we cannot drive the spin transition, and that's why we only observe 4 fine spin transitions there. So here, what's very interesting that by performing spin spectroscopy at single defect-scale, we're able to have a signature of a motion of a single atom inside this bulky macroscopic silicon sample made of billions of atoms. So with that, I'm going to conclude. So first, for the G centers, we're able to integrate them into photonic cavities while preserving a good single photon purity. We're also able to measure the nonlinear spectrum on single G centers, demonstrate the coherent control, and we evidence this single spin tumbling effect that we believe have never been reported on single spin scale. So now, what's next for the G centers? So concerning like quantum applications, so the electron spin is not going to be a very good memory qubit because its coherence time is going to be ultimately limited by the lifetime of these states. So there, you want to use nuclear spins as memory qubits. And the advantage of these structures is that in the ground state, you have no electron spin. So it cannot dephase the state of nuclear spins. And as a result, we could achieve very long coherence time. Similar to what have been observed for ionized donors in silicon-28 with 4-hour coherence time. Another interesting step that we want to investigate is how to control the spin tumbling mechanism. Because here, so the rotation, we believe it's triggered by the band gap excitation. But if we switch to resonance excitation, here, the direct transitions have to follow selection rules. And in principle, we should be able to lock the position of the atom, silicon atom, on one given site. And also the different other rotations, dynamics that can be investigated. So here, the fact that we're observing these fine Swiss structures, it indicates that all the orientations are non-equivalent because the G centers undergo some perturbation, external perturbations. But if we remove this perturbation and come back to the unperturbed perfectly symmetric G centers, there the silicon can move between sites by tunnel effect. And we can have a perfect delocalization of this atom and reproduce exactly the energy level of the benzene molecule. We could also try to investigate the classical dynamics like top-like rotations by trying to increasing the temperature. After we're just going to flash, I still have a few minutes, flash some results we got on another defect. It's called the W centers. So this defect is an intrinsic one. It's made of 3 interstitial silicon atoms. And we were able to isolate those defects at single defect scale. And the interesting things of the W centers in that they have a very sharp zero photon line, around 1.12, 18 nanometers, and there's 40% of the emission directly into this zero photon line. And our colleagues from Syria Grenoble, they developed a new method to deterministically position the single W centers at the core of photonic cavities. And with that, they achieved a record of 1.3 million counts per second on single photon emissions on a single integrated W centers. So it's not bad because it was the first demonstration of single W centers integration. Okay, and so now on a more, I would say, broader view. So the main challenge for all the different color centers in silicon is to control the optical interface. Because, and especially to achieve indistinguishable photon emission on long term. Because here, we're not dealing with real atoms trapped in a vacuum environment. Here, we're really at the solid state. So all the defects are going to experience a slightly different static environment, resulting in spectral shifts. In addition, you can have dynamical noise, like dephasing due to coupling with phonons, also spectral diffusions that are going to produce broadening and also spectral wandering. And currently, the indistinguishable photon emission has been only demonstrated on short-term scale. So for instance, here, I show you the Hangul-Mandel experiment performed on single integrated G centers. And we can see that the coherence time of those photons is very short, on the order of like few nanoseconds. So still, by using temporal filtering and collecting only these photons, you can trick that. And this kind of temporal filtering has been used in the spin-pin entanglement that I showed you at the beginning of my presentation. And for instance, here on single integrated T centers, they were able, by performing some conditional measurements, to show that the lines over time of the single T centers were really going around over like a few gigahertz range. And also what is pretty hard is that all the integration of the defects degrades the optical coherence time. So it's really, I believe, where the community will have to put a lot of efforts in the next years, try to also improve on the engineering of the defects in order to create a very nice environment to have coherently optical coherent defects with nice spin properties and photon properties. So with that, I think I'm at the end of my presentation. So I would like to acknowledge all the people from the from the solid state quantum technologies group in Montpellier that were involved in the silicon findings. And also here, so all the spin control and development have been developed by Félix Cache during his PhD. And I would like to also thank all our precious collaborators from Grenoble for all the nice samples they provided to us. And with that, I would like to thank you for your attention.